So they've got the iFocus working, so we'll probably use those a little bit today. I'll try to get those uploaded, if not this afternoon, some early in the day tomorrow, so we can kind of make sure that everyone's registered correctly and that the scores are going to upload okay once we kind of start actually getting more of these class iFocus days. I believe we left off kind of talking about the relationship between the mean and the median and how that kind of defines the skew of our distribution. We said that when the mean is to the left or less than the median, that reflects we have this long left tail or some really small values that draw that thing down. We've got this left skew distribution. If the mean is to the right or is greater than the median, that means we have extremely large values that are pointing that mean to the right, and we kind of have this right skew distribution. So the next thing we're going to talk about, some of these descriptive statistics are going to be measures of dispersion. All right, so last class we kind of focused on where's the middle part of the data, right? When we're thinking about mean, median, mode, we're looking for where's kind of the middle part of the data. Now we're going to think about, now that we know where the middle part of the data is, how much does the rest of the data set vary from that point, right? So when we say dispersion, you can also think about kind of variation in the data. So the very easiest, kind of measure of this is simply to look at the range. Right? So the range is just going to be, you take the highest value, subtract the lowest value, and that's the range of your data, right? Now the data set goes from, we had a data set that went from, let's do it like this, 1, 2, 3, 4, all the way up to 100. The highest value is 100, the lowest value is 1. So our range would just be the difference between those two. Right? So if I have a small data set like this, right, what's the highest value that I have in that data set? 90, lowest value is 20. So I just take the difference between those two. Right? So this is okay. This blue marker is kind of light, so let me try using this screen instead. So the problem is, what if I had another data set over here? This one's light too. Brand new markers, so hopefully maybe they'll get darker as we go. That looks something like this, right? Where instead of going from 1, 2, 3, 4, all the way 100, it was all ones, and then one observation was 100. What's the range of this data set? Highest value is 100, lowest value is 1. It had the exact same range. These are clearly two very different data sets. There's a lot more variation here, right? Just look at, you've got numbers 1 through 100 as opposed to 99 ones and then 1 100. There's a lot less variation in that data set, and the range can't capture that, right? So it's kind of a good starting point, but it doesn't really allow us to capture the entire variation that exists in the data set. So we're gonna have to go a little bit further. The kind of statistic that we'll focus on pretty much the entire class today is the variance. Okay. So here's kind of the mathematical formula. I'll try to walk through this. So I know we're going to start using some more mathematical notation. So it's kind of remind us what some of this means. So sigma squared is how we're going to write the variance. So that's sigma squared. That's going to represent our variance. And the equation is this. So we had a little bit of experience last class with that summation sign. So start from the very first observation. Do what's ever on the right there. So we'll talk about that in a second. Do that for every single observation up to the nth, right? Capital N, which is the last observation in our population data set, and then add them all up. So what is that thing to the right of the sum sign that we have to do for every observation and add them all up? Well, we're going to look at the value that first observation has for that X variable we're interested in. And we'll take the difference between that value and whatever the mean of that X variable is. So let's work with a easy data set, and I kind of walk you through this, and I think maybe this will make a little more sense. So let's say I've got a data set that looks something like this. If you can't read this, let me know. I just grabbed these little markers and I'll go faint. So 2, 4, 6, and 8. Right? That's my small data set I have here. I wanted to find the mean of this data set. And actually, yeah, we'll do this. So 2, 4, 6, and 8. The mean would be what? Add these up, we get 20, divide by the number of numbers I have. So the mean, 20 over 4, or the mean is 5. Okay? So what I'm then going to do is go through every single observation, subtract the mean, right? Take that x value and subtract the mean. We'll call that the deviation from the mean. And I'm going to take that deviation from the mean and I'm going to square it, right? So I'll break this down into parts just so we can kind of think about it. So I've got, take the x value and subtract the mean. So 2 minus 5, -3, 4 minus 5 is -1, 6 minus 5 is 1, 8 minus 5 is 3. I'm going to write this over here since we already have it. Let's get it out of my way. There we go. That one's all perfect. So the next thing I'm going to do is take that deviation. I'm going to square it. All right. So -3 squared is 9. -1 squared is 1. 1 squared is 1. 3 squared. I'm then going to add all those up. So 1 plus 1 plus 9 plus 9 is 20. That's my numerator. That's the sum of all the deviations squared. Right? I went through each observation, took the deviation, squared it, added them all up. The final step I have to do is still divide by the number of observations. So divide by 4 here. This is a weird one where a variance is the same as the mean. That's just coincidence because it's a small data set and I chose, not small numbers. Okay, so you can kind of see here, anytime we have values that are not very far from the mean, right? First of all, when we square this, it doesn't matter if I'm above or I'm below the mean. Each one of those observations is evidence of variation in the data from that middle point. Each one of these varies from that mean. And the ones that don't vary by much, right? Once we square them, they don't end up adding very much to that numerator because those observations aren't, strong evidence that there is a lot of variation in the data set. However, for values that are further from the mean, if we just look at how far away they are, yeah.
What's the set at the top of the -3? I can't see.
We're just taking the deviation there. Yep. So observations that are further, right? Instead of just adding like 1 or 3, when we square it, not only does it make everything positive, right? Because a negative times a negative, positive times a positive is a positive value. So right, it doesn't matter if we're above or below the mean, it's still evidence of variation. But the further we get from the mean, when we square that value, notice 1 becomes 1, but 3 becomes 9, right? So by squaring it, not only do we make everything positive, but we also over penalize observations that are very far from the middle point of that data, right? So if we have really extremely large values that are very far from that mean, kind of really gets over penalized in that variance equation. Or it's just very strong evidence that there's more variation in the data set. Okay. Any questions over anything? So one thing I want to try to connect with what we were doing last class too. So let's say we've got our equation for the mean. Another way we could write this, we said, was x1 plus x2 plus x3, so on and so forth. I'm going to actually do one where we just stop at 4. So we would then be dividing by n, where we're going to have 4 values. Just kind of make this point. I could rewrite this as something like this. Okay? Where each observation is being weighted, it's 1/4 of the entire data set, right? Each observation will be 1/4. Now, if we did this more generally, it would just look like this. All the way to whatever that last observation is. So kind of hiding behind the scenes is that each observation in the mean was being weighted the exact same amount, 1 out of however many observations we had. The same kind of thing exists for this variance, right? So if I want to, I think I'm probably not going to do it here for a second. So if I think about what I would have here, okay. And I would add to that the second deviation from the mean squared, so on and so forth. But because I'm dividing by n here, it's the same idea as the mean. I could just pull this 1 over n out and put it in front of every single deviation. So it's almost like every single observation is going to be some evidence of how much variation there is in that data set. How much variation comes from this observation? How much variation comes from this observation? But then we all weight them equally, which is 1 over n, right? So each one kind of has the same influence, or at least the same power over that variance. Now, some of them are stronger evidence of variation, so they add larger values to that numerator, but whatever that value is, it's still weighted by 1 over n. Okay? I've got setting us up for something that we'll probably talk about on Friday. I don't think we'll get there today. And this is, might make a little more sense kind of next class why I'm kind of hammering this a little bit right now. Okay. Any questions here? So if I'm calculating a population variance, it's kind of, we just walk through the procedure. If instead I only had sample variance, and for now, you're probably going to kind of have to just take my word for it. We'll get more into why we have to do this when we get to confidence intervals and hypothesis testing. But if we only have sample data and we're calculating a variance, it's the exact same process. We still go through every observation, take the deviation from the mean, square it, add them all up. But instead of dividing by the number of observations in our data set, we divide by the number of observations minus 1. Okay? So the idea behind this, once we took confidence intervals and hypothesis testing, is that we know our samples, think about it this way. If I have a large enough population data set, dividing by 10,000 instead of 9,999 isn't going to be that much of a difference. But most of our samples, right, they're samples, so they're smaller. And if I have something like 10, right, I have 10 observations, it's going to influence, even if I could observe the population data, how much different the variance for my sample would be. So we'll get into it a little more with confidence intervals. So basically, the size of my sample dictates how far off my sample variance would be from the population variance, even if I was able to observe both. So for now, just know that instead of dividing by n, we have to divide by n minus 1. And to give a little more insight as to what this kind of does, let's say I added up all the deviations from the mean squared, and I get 20, right? That's kind of from our example. So if it was a population variance, I would do 20 over 5. No, I would 4 observations, right? 20 over 4, and we got a variance of 5. Let's now say instead I tell you, well, actually that wasn't population data, it was only sample data. So you should have been calculating a sample variance, which you'll still get that same numerator. The numbers haven't changed, right? We still have that same data set. So when we go through and find a deviation from the mean squared, that's going to be the same. But now we're going to divide by n minus 1. So instead of 4, we're going to divide by 3, right? We're going to get something what? Something just below 7. It's a little bit lower than 7. So that's why I didn't approximately, because I don't want to pull a calculator out. I can't do that. I probably would do it in my head, but it'll waste time. So notice when we divide by n minus 1, we're counting that sample variance, we're kind of erring on the side of caution. We're always going to be inflating the variance a little bit more, right? And this is the idea once we have the confidence intervals. We're making sure that we're not making statements that are not, I don't want to say not true, but for now we'll say that aren't true, right? That we need to make sure that we treat the data as though it has a larger variance than it does, because it's only sample data. Okay? Dividing by a smaller number, it's always going to overinflate that variance for our sample. And then the units of our variance are just whatever the units of our variable are, so that's nothing crazy. So I wrote down the steps here, just kind of in words, what we did, right? If we want to find if the variance is, this isn't really, you probably won't find the definition of textbook, but I think a good way to think about the variance is it's a measure of how much variation exists across all the observations of the data set. How much variation from the mean or the middle point of the data exists across every observation in the data set. So to find that variation from the middle point or the mean, we first need to find the mean, right? Then we go through, subtract the mean from every observation, we then square each one of those deviations. Now, if you want to combine those steps, you can. If you want to do it all at one time, right? It's not that difficult. Instead of having that column where it was what? negative 3, negative 1, 1, 3. I could have skipped that and just taken, 2 minus 5 squared. Oh, that's 9. Write that number down. But I could have kind of wrapped that up in one step. If you break it up into steps, it makes it a little bit easier, and it also kind of clarifies this idea of like, oh yeah, when I square it, it's treating things above and below the mean the same. It's over penalizing things that are very far from the mean. So that's why I kind of show you how to do that, separating all those steps. And then finally, we add up all those deviations squared, and for population, we divide by capital N, the number of observations of our population. For our sample, we divide by n minus 1. Okay. Any questions or anything here before we keep moving? Okay. So the next measure of dispersion or variation we have is going to be the standard deviation. This is the exact same thing as the variance with one added step. So once you have the variance calculated to get the standard deviation, all you're going to do is take the square root. Right? So that's the exact same equation I was showing you on the other slide for the population and the sample variance. It's just that I've added one more step, which is I took the square root. All the standard deviation is, it's scaling the variance down. Right? So it's scaling the variance down. And the reason why we talk about it now is because down the road, it becomes very useful for things like confidence intervals and hypothesis testing. Okay? So I have the example up there, right? But if the variance is 100, we would just take the square root. The standard deviation would be the square root of 100 or 10. You kind of, if you want to think about it, if I take the variance, if I take the square root, that's going to cancel. Everyone has different math backgrounds, but taking the square root is the same thing as going to the 1/2 power. You can kind of take this, and so then it's really just sigma to the first power, which is just itself, right? So basically that taking the square root of a square cancels that out. Okay. Any questions on this? Shouldn't be too bad here. So we'll get some more practice with it. So let's say I had a data set that looks something like this, right? So this is like an old, I don't know, early 2000s, early part of the last decade. I grabbed a bunch of, or the star put out a bunch of salary data. I'm also football coaches, so here's 10 of them, right? So I'm going to treat this as population data, since it was everyone that they put out that was kind of had a salary from the university. And you can kind of see, the bulk of the data, right? 76 to 150, that's a pretty small range. But then we're going to have a pretty extreme outlier here for the head coach, and then kind of one employee, the video tech guy, not getting a lot of love, right? So we've got some variation in this data set, but how much? Okay. So let's say I wanted to, if I want to find the variance, the very first thing I need to do is find the mean. The variance is a measure of how much the data set varies from the mean. Okay. So if I had this data set, how would I find the mean? No one? Yeah.
Add all the numbers up and then divide it by the amount there.
Yeah, right. Just add all these salaries up and divide by however many there are. We count them, there's going to be 10. That might makes it nice and easy. So I go ahead and add them all up. I divide by 10. Hopefully that's not too bad. Right? The silence is making me worry about how the rest of the semester might go. Right? We've got to be able to calculate these means. So we add every number up, divide by the total number of numbers we had. We've got our mean. What if I then want to find my variance? So if I want to find the variance, you're going to have to go through, take every single coach that I have here, take their salary, subtract that mean of 134.5, and it represents thousands, and then square it. Once I do that for every single observation, I'll add them all up and divide by, I'm treating this as population data, I would divide by 10, right? Just n. I don't have to do n minus 1 because it's not sample data. So that's what this would kind of look like if I type this all out in my calculator and didn't do it observation by observation. I could do this all as one line on my calculator. It's just easy to make some mistakes sometimes with the parentheses or maybe forgetting to square one of them. That's why kind of breaking it down observation by observation, I think, is a little more of a fail-safe way of not making mistakes. But once we get more comfortable with it, we'll probably be able to enter it, especially if you have like a TI or 83 or whatever they are. Pretty easy to enter it in at one time. Any questions on kind of just that process? Showing you another example here. All right, so we get about 14,700. You know, I could break this down and create a whole new column. I think this is a good way to do it when you're working out on hand. All I did was go through and find the deviation squared for every single one of these coaches. Okay? So notice, I mean, 134 was the mean, so the values really close to the mean aren't adding a whole lot to my measure of variance, because those were two observations that didn't provide me much evidence that there was a lot of variation in the data. However, once I get to some of these values that are further away from 134, further from the mean, notice I get, instead of 240, up to like 8,000 and adding that variance. And then of course, I look at the most extreme value, it was pretty far away from the mean. And once I square that, I'm adding 120, that's a 125,000, because that's an observation that provides strong evidence that there's quite a bit of variation in this data set. Right? So another way to think about this is, when you're finding the mean, what you're really saying is, okay, each one of these values should kind of count as 1 over n, right? 1 over n of this overall mean. That's how much influence you have. So I'm finding the average of those x values. Well, I'm really doing the same thing. Well, I had it up here. I'm really doing the same thing when I look at the variance, because I'm saying now it's not just x value, but what I'm kind of finding is the average deviation from the mean squared. Because I'm weighting everything by 1 over n, just like with the mean, but now instead of just the values being weighted by 1 over n, it's the deviation squared being weighted by 1 over n. So I'm kind of finding the average variation in the data set. So, you know, that head coach, he's strong evidence of a lot of variation, but it only is kind of counts as 1 over n, right? And so if you have more observations that don't provide strong evidence of variation in the data set, they're going to kind of outweigh, right? There's going to be 5 or 6 observations here that don't add a lot to the variance. And so they'll kind of like cancel out that one extreme value. Just like if you had a data set where, you know, the majority of people in the data set were, say, I don't know, 5'8" to 6 foot, but you had one person who was 7'2". Well, if I've got 20 people who are kind of in that shorter range, they're going to kind of outweigh that one person that has an extremely high height. And when I look at the average, right, the average is going to be closer to like 6 foot instead of that 7 foot. Right? So same idea here for the variance. Once I add up all those deviations, divide by my number of observations, and notice kind of the average deviation from the mean is only about 14,000. So that one observation that added 125,000 in the numerator, it was kind of, you know, there's a lot of other observations to kind of draw that average deviation from the mean down a little bit. Okay? That's a different way of thinking about the variance.
When we get questions about these, will you tell us what the sample population?
Yeah, right. If you have to know, you have to be told whether or not you have a population data set or a sample data set. Otherwise, how the hell are you supposed to know, right? So yeah, you'll always be like, usually like on an exam or things like that, it'll be like sample, all caps, bolded, right? So I try to make it very clear because that's, yeah. Any other questions at this point? We're out of time. Oh. We're going to skip fun with the variance for right now. I'll probably come back to that. We'll start on next class with it. Skip down through this a bit. I want to try to get these eye clickers going, and I will. Let's see. Would help if I had it opened up. See if we can get them to work today. So we are section 3. So I had the one in my office working, so we'll see if I have it set up correctly. You guys, is it showing up today on AA, or is it your icons looking up? Yeah.
Working on VPs.
Oh, because I was messing around with it at the end of last class, wasn't I? Let's do AA. I'll always leave on AA. I forgot when we were trying to troubleshoot it last class, I switched this and it must have saved. All right. Now it should be good to go. So I'll give you about a minute and a half, 2 minutes to kind of work on. I'll give you about 2 minutes to work on this. I'll kind of talk a little bit. But let's assume we have a population data set here, and you're going to try to find the population variance for this data set. We've got 7 observations. I kind of saved you a little time. Remember from last class, we calculated the mean was 45. Okay. So if you know the mean is 45, I want you to find the population variance. I'll give you a little bit of time to work on that. Still working on spine. Let's kind of talk a little bit. So, what's kind of the first step we should be doing? Going through each observation, doing what? Subtract the mean. Right, and then after we subtract the mean for every observation, we should then square that value. Once you have those 7 deviations squared, right, one for each observation, you'll add them all up. And we'll divide by something. I won't tell you what we'll divide by. There's a population data set. So all right. So in this one, I'll be nice. We'll kind of start talking through it, right? So works. There you go. That's right. Probably the easiest way to do this is set up a column, and especially if you're like on the exam where you have it in front of you, maybe write the numbers down, write down your deviation squared for each one. So 20 minus 45, that's what? Negative 25. Square that, write that number down. Then go to the next observation, 35 minus 45, negative 10. Square that, write that number down. Go through every observation, write those deviations squared, add them all up, and then for a population, divide by the number of numbers we have. All right. We're looking at those answers A through D there. Hopefully everybody gets this one correct. Okay. And so if we're looking at those answers A through D, hopefully we get this one correct. All right. So I'm going to close this out. We'll make sure we get an answer in. Yeah.
Are you peculiar on how like you want our decimal place format, or will you just?
So like on this one, right? It's kind of nice because we didn't have any any decimals. If we're working through a problem in class, it's likely I've chosen numbers that the decimals not be an issue. When it comes to the exam prompt,
Or this one has decimals.
if I display, so when I display it, right, when I say the decimals don't matter, I'm never gonna give you like 414 point, I don't know what it ended up being, 17 or 414.18. Like it'll always be, and they're gonna be more than like one integer away. If there's a decimal and I'm showing you just the integer value, choose whichever one's closest. And I won't ever have two where like, you did. On the exam, we'll talk a little bit more about that when we practice exams as we get closer. Usually that's kind of a similar idea. Maybe I'll leave the decimals. I have to cut them off at like the second decimal, but I'm never going to give you two answers where they're only off by the second, right, at a 10th space. So yeah. Any other questions on this one? Hopefully, like I said, sometimes I'm nice in these eye clickers. I want it to be hard. Obviously, we should have been paying attention. I showed you the answer, so we should have gotten this one correct. Now I'm looking at these values. And just out of curiosity on this one, well, I won't use this question, but which one of these could you have definitely ruled out right away, and why? Right? If it's 0, what would that data set have to look like? So let's think about what a variance of 0 would mean. Huh? Yeah, it would mean there's no variation. Every observation provided you evidence that there was 0 variation in the data set. So if every deviation from the mean squared is 0, that means every observation would have to be equal to the mean, right? The deviation from that mean would have to be 0. So, we could have maybe one observation where it provides 0 evidence, right? Every single one providing 0 evidence would mean we have the exact same number. So all 5s, all 35s, all whatever it was, all the same number, right? It's not very likely we're going to be working with a data set like that because it's not a very interesting data set, right? So I want to kind of point that out. Also, that the variance can never be negative because when we square these values, right, the numerator is always going to be adding positive values. Once they get squared, everything is just positive, right? And the number of observations is always going to be positive. So our variance has to be 0 or higher. And it's very unlikely it will be equal to 0. Oops, I'll kind of already give you a sneak peek there. So let's say, and this one shouldn't be too bad, right? But let's say instead you have the same exact data set, right? Go back, the data set's exactly the same, right? So we can walk through this process, find that some of those deviations squared, it's going to be the exact same. However, now I tell you, actually, it wasn't population data, it was sample data. And I, said, you're going to have to change your calculation. I now want you to find the sample variance. So I'm not going to give you near as much time, maybe next 20, 30 seconds to think about this, because it should be pretty clear what the sample variance is going to be. You have the values from the last problem, right? You already know that some of the deviations squared here. That's not going to change. There's only one thing that changes for the sample variance. Should be able to find what that sample variance would be pretty quickly. We've got another 10 seconds to 120. All right. If you haven't gotten an answer in, went in now. I thought we had 31 last time. There we go. So why should I have been able to do this very quickly? It's the same exact process. My data hasn't changed. So I know when I add up those deviations squared, I'm going to get the same 2,900. Right? Now, instead of dividing it by 7, right, I'm going to divide it by 1. So if I'm dividing by a smaller number, which I knew because I knew that, okay, if it was sample data, I should have been dividing by n-1. So I should have been dividing the same value by a smaller number. I know that my variance now is going to have to be greater than 414, or greater than what it was when I was dividing by just n. So the only value here greater than 414 is 483, or I could have just taken that same 2,900 numerator. Now I'm dividing it by 6. Okay? Yeah.
You divide by 6, there's 7 employees there, and then you can always do -1, that, so if there's like 8, and you divide by 7.
Yes, and the only reason it's never going to be like this. I mean, sorry. I'm using kind of a weird example where I said, here's the population data. And I said, wait, I was wrong. So you shouldn't have been treating it as population data. You should have been treating it as sample data. So instead of dividing by n, you should have been dividing by n-1. Usually ahead of time, like either way, and it doesn't just like change. I'm just kind of using it as an example so we can work out the same data and kind of hammer this principle of when I'm dividing by n-1, that's really going to just overinflate or kind of increase that variance calculation.
So population is -1, sample is,
Population, we don't do anything, just divide by n.
and then
Sample, you divide by n-1.
Okay.
Yep. When I have sample data, think of it as I don't have the whole picture. I want to err on the side of caution. So instead of dividing by n, when I divide by n-1, it makes my variance a little bit higher. Right? Any other questions on this? So sometimes I'll do these with these 5 clickers, right? It's more of like a concept or a principle. It's not that each one we're going to have to do completely new computation. I mean, you could have went through and found the deviation squared again. You're going to do the exact same. So if you just kind of are recognizing that's the same process to calculate a population sample variance, it's just that with a sample variance, we divide by n-1, you can err on the side of caution because we don't have the entire picture. No, we don't have the entire population data. Any other questions on this? Okay. So what do I want to do today? We've got 15 minutes left. Go back here. We'll touch on a little bit of this next class. So we had the old way of calculating the variance. There's actually a second equation that you might see sometimes used. It's not, I don't usually like to kind of do too much with it. I won't ask you questions about it like on Excel, or you don't have to use this method on any homework assignment. Just to kind of show you, if anyone likes math, it's a very small number of people I found out is teaching stats, but this is kind of interesting, right? So this is kind of the equation we have for our sample variance. We actually could rewrite this equation to look something like this, and it would give us the exact same answer. So all I'm doing here is I'm taking each observation's value, squaring it, and then adding them all up. And then I'm going to subtract the number of observations times the mean squared. And then the divide by n-1, I just pulled it out front because I'm going to do something mathematically here where we can just kind of keep that out in the front and just work with what's in the kind of brackets. So I'm telling you these will give you the same answer. You can actually go through and do this. I'm going to skip through the proof and come back to it. But if I went through that same data set, squared every single x value, and then added them all up, right? That was the first component we did. Then take, look, the mean got knocked over a little bit, but then I take the mean squared, plug in the mean squared, plug in the number of observations 10, plug in the sum of the x's squared. I would get the exact same value, and I still have to divide it by n, right? So I still have to divide it by 10. I'll get the same value I did before, right? I think it's a little bit more of a, I don't know, trickier, convoluted way of finding it. And it also doesn't hammer home really what the variance is measuring, which is the average deviation from the mean squared. And so that's why I don't waste a lot of time on it, but it will give you the same answer, right? It's kind of interesting. You go through the mathematical proof. Anytime I tell you something, sometimes I'll show you why. You won't ever have to reproduce this. So if you want to tune out right now, I guess you can. If you're mildly interested, I guess keep listening. But right, we can do the kind of math here. So just take that numerator and start, I guess we'll put what we call foiling, right? So xi times xi is xi squared, xi times x bar is xi times x bar. All right, so just write that out. One nice thing about the sum sign, anytime I'm adding or subtracting things, I can actually then just distribute that summation sign. So now you can kind of treat these as 4 different sums of 4 different things. From here is where it gets kind of interesting. So anytime I have just a constant value, so the mean squared that's just gonna be some value, it might be 100. So if I put a summation sign in front of a number, so go from 1 to n, well, that means take the number 100, starting with 1, then add it another 100, add another 100, all the way up to the nth time, right? So anytime I have a constant, the summation sign really just means take whatever I'm adding up and multiply it by n. So here, this last guy is just n times x bar. I'm then going to do kind of a tricky thing here, where I just multiply each of those by n over n. Multiplying something by n over n is just multiplying it by 1. So I haven't changed anything. But by doing that, I can start to rearrange some things, right? So anytime I have a constant, I can pull it out in front of that sum. So I'll just pull out n, because that'll just be some number, right? I then can say, well, x bar, that's just going to be some number as well, so I can pull that out front. Now notice I've got the sum of the x's over n here. What does that represent? That's just I add up all the x values, divide by the number of x values I have. That's my mean, right? So that's just x bar. So these become n times x bar squared. We had over here as well. 2 of these will cancel. And I've got that formula I was showing before, where I take the sum of the x squared, subtract n times the mean squared. And then there's that n minus 1 that we kind of pulled out when we try to make this proof. So it's just a different way of doing the same thing. I think it's a little bit more of a tricky way. It doesn't really hammer home the principles. So I only really do it if we have time, which we had a little bit today. So kind of walk through that. So anytime I go through a proof or something like this, don't think you're ever going to have to recreate it or kind of talk about it or anything, right? I'm just kind of showing you a handful are interested, right? If you ever want to talk math or are more interested, always feel free to reach out and talk, right? I'll waste time talking about that math. So we already worked through these. So the last thing I want to go through, I'll keep this up here, but I'm going to draw my own as well. So it's going to be hard because none of these markers are working real well, but we'll do our best. Right? So let's say I have this distribution, right? And let's say that the variance is, I don't know, 100, and the mean is 50. Then let's say I have another distribution. Let's see if I can get the blue one to be a little bit darker here. That has a lower variance. Okay. So I've got another variable that has a lower variance, but it has the exact same mean. When I'm thinking about its distribution, that means it's going to be centered around the same point. However, because it has a lower variance, that means it's going to be, there can be less variation or it's less dispersed. So it ends up being true. But if it has a lower variance, that means that values that are close to the mean are more likely for us to see. Remember, when I'm thinking about here on my y-axis, I'm plotting kind of the frequency, right? That's how I got my frequency distribution. Okay? So with a lower variance, what that's telling us is that the values that are really close to the mean are more likely to be seen in this data set. And if there's less variance, that means the values that are further away, way out here, they're way less likely for us to see. So another way of thinking about this is on the flip side, right? If the variance gets higher, right? Going from this blue to the black distribution, if the variance is getting higher, that means the values really close to the mean become less likely for us to see, and the values further from the mean become more likely or have a higher frequency. So kind of the visual I have here, I've got not just 2 distributions in the slides, but I've got a bunch. Notice starting from this blue line going down to, I don't know, gray. I can't, is that gray? Looks like it. As my variance gets higher, right, my variance is getting higher here, that distribution is getting flatter, right? Because as the variance gets higher, the values kind of in the middle become less likely. So I start getting kind of this flatter curve where the middle part isn't as high, but notice the values further from the mean are becoming much more likely. Okay? So higher variance flattens out your distribution. A lower variance, right, kind of peaks that distribution because the values right around the mean are very likely from the C. Any questions on that? What is a different mean going to do to my distribution? So we've thought about as the variance gets higher or lower, it flattens or kind of peaks that distribution. What if I had two distributions with the exact same variance, but one of them, so let's say we've got same variance, but the mean is 50 here, and for the blue line, we're going to do a mean of 100. So if a distribution has a higher mean, what's that going to do? So here's my first one. Mean of 50, variance of 100. For the second distribution that has a variance of 100, but a mean also of 100, what's going to happen to this distribution? Yeah, right? It's going to have the exact same height, right? Because it's the same variance, but has a higher mean, so it's going to shift it along the x-axis. So higher or lower means just shift you along the x-axis. Higher or lower variances kind of change the height of your distribution on the y-axis. Okay. Kind of keeping those two things kind of in check there. Also, is a point to help you throughout the semester. If I'm doing something like this on the board, I'll probably take some notes on it or like kind of listen to these things just because you can never kind of go. I mean, I guess I do record these, but you're obviously not going to see what's on the board. So might be a great idea for note taking to kind of really focus when I'm doing some of these things on the board. Because there are additional examples that I think are pretty helpful. Yeah. Yep, higher or lower mean will shift us along the x-axis. Higher or lower variance kind of changes how high or how low our distribution is, how flat or how peaked it is on the y-axis. Before we get out of here, we've got a couple minutes. So I'll get those iClicker scores kind of uploaded. Like I said, hopefully this afternoon, or the latest tomorrow morning, so we can make sure those are working correctly. I'm going to put out a video I recorded yesterday. That's going to be what we cover on Friday. So it's going to introduce the topic to what we're going to start covering on Friday. So I think it ended up being 4 minutes long or something, so pretty short. It's me introducing an idea, working through an example. I'll probably start out with a question or two on Friday that's related to that video, and it allows us to kind of get an easy example out of the way and jump into what I think is kind of some more valuable things. Okay, so look for that. I'll have that posted on YouTube right around 2 o'clock today. Other than that, we'll see you guys on Friday. Absolutely.